In the annals of scientific exploration, the double-slit experiment stands as a beacon of quantum mystery. Its origins trace back to the early 19th century when a brilliant English polymath named Thomas Young first unveiled the wave-like nature of light. Young's apparatus was strikingly simple: a beam of light, a screen with two closely spaced slits, and a backdrop to capture the resulting pattern. Young's genius lay in his interpretation of the results. If light were composed of particles, as Isaac Newton had proposed, the screen behind the slits would display two distinct bright bands corresponding to the two openings. Instead, Young observed a series of alternating bright and dark fringes, a pattern known as interference. This phenomenon could only be explained if light behaved as a wave, with peaks and troughs interacting to create regions of reinforcement, bright fringes, and cancellation, dark fringes. Young's experiment, published in 1801, sent shockwaves through the scientific community. It directly challenged the prevailing Newtonian view of light as a stream of corpuscles. Despite initial skepticism and resistance, Young's findings ultimately ushered in a new era of understanding, establishing the wave theory of light as a cornerstone of classical physics. The scientific community initially met Young's wave theory with skepticism. Newton's corpuscular theory, after all, had held sway for over a century. Newton's reputation and the intuitive appeal of particles in explaining everyday phenomena made it difficult for scientists to embrace the more abstract concept of waves. However, the elegance and explanatory power of Young's experiment gradually won over the skeptics. Further experiments and theoretical developments throughout the 19th century solidified the wave theory's dominance. James Clerk Maxwell's groundbreaking work in the 1860s, unifying electricity, magnetism, and light as manifestations of electromagnetic waves, marked the triumph of the wave paradigm. The victory of the wave theory had profound implications. It not only revolutionized our understanding of light, but also paved the way for advancements in optics, telecommunications, and our understanding of the cosmos. Yet the story of light and the double-slit experiment that revealed its secrets was far from over. As the 19th century gave way to the 20th, a young Albert Einstein would once again turn the world of physics on its head. In 1905, Einstein published his groundbreaking paper on the photoelectric effect, a phenomenon that defied explanation by the classical wave theory of light. The photoelectric effect described the emission of electrons from a metal surface when light shone upon it. Einstein's genius lay in proposing that light, in this context, acted not as a continuous wave but as discrete packets of energy, which he called quanta and which later became known as photons. These photons, Einstein argued, carried specific amounts of energy proportional to their frequency. When a photon struck the metal, it transferred its energy to an electron, giving it enough energy to escape the metal's surface. Einstein's explanation of the photoelectric effect, which earned him the 1921 Nobel Prize in Physics, marked a turning point in our understanding of light. It resurrected the particle view, not as a replacement for the wave theory, but as a necessary complement. Light, it seemed, could exhibit both wave-like and particle-like behavior, a concept known as wave-particle duality. If the dual nature of light was surprising, the next chapter in the double-slit saga would prove even more astounding. In 1927, Clinton Davison and Lester Germer, two American physicists at Bell Labs, were conducting experiments on the scattering of electrons by a nickel crystal. To their astonishment, they observed a diffraction pattern similar to the interference patterns produced by light waves, but with electrons, particles of matter. This unexpected result provided compelling evidence that electrons, long considered tiny particles, also possessed wave-like properties. The wave-particle duality, once thought to be a peculiar feature of light, was now extended to matter. The implications were profound, challenging the very foundations of classical physics and ushering in the era of quantum mechanics. To Section 5, Feynman's Wisdom. Embracing the quantum enigma. The double-slit experiment, with its ability to reveal the wave-particle duality of both light and matter, became a central puzzle and a source of profound insight in the development of quantum mechanics. Richard Feynman, the legendary physicist known for his clarity and playful approach to science, considered the double-slit experiment to be the heart of quantum mechanics and a phenomenon which is impossible, absolutely impossible, to explain in any classical way. Feynman's approach to understanding the double-slit experiment involved embracing the inherent strangeness of the quantum world. He argued that instead of trying to force particles like electrons into either a wave or particle category, we should accept that they can exhibit both behaviors depending on the experimental setup. Feynman developed a way of visualizing quantum behavior using what are now known as Feynman diagrams. These diagrams, while not literal depictions of reality, provided a powerful tool for calculating the probabilities of different outcomes in quantum experiments, including the double-slit experiment. Perhaps the most mind-boggling aspect of the double-slit experiment emerges when we try to determine which slit a particle, say an electron, actually passes through. If we place a detector at one of the slits to observe the electron's path, the interference pattern on the screen disappears. The act of observation, it seems, forces the electron to choose a single path, destroying its wave-like nature and collapsing the wave function. This phenomenon, known as the observer effect, lies at the heart of the quantum measurement problem. It highlights the profound difference between the classical and quantum worlds. In classical physics, observation is passive. It does not affect the system being observed. In the quantum realm, however, observation becomes an active participant, influencing the very nature of reality. The observer effect raises profound questions about the role of consciousness in quantum mechanics. Does consciousness cause the wave function to collapse, or is there another, deeper explanation for this strange phenomenon? These questions remain a subject of intense debate and ongoing research in the foundations of quantum mechanics. While the philosophical implications of the double-slit experiment continue to be debated, its practical applications are already being realized in the burgeoning field of quantum computing. Quantum computers exploit the principles of superposition and entanglement, phenomena deeply rooted in the wave-like nature of quantum particles, to perform calculations that are impossible for even the most powerful classical computers. Unlike classical bits, which can only exist in one of two states, 0 or 1, quantum bits or qubits can exist in a superposition of states, simultaneously representing both 0 and 1. This unique feature allows quantum computers to perform computations on multiple possible values at once, giving them an exponential speed advantage for certain types of problems. Quantum computing has the potential to revolutionize fields such as medicine, materials science, and artificial intelligence. By harnessing the power of the wave function, we are entering a new era of computation and unlocking possibilities that were once confined to the realm of science fiction. The bizarre implications of the observer effect are vividly illustrated by Erwin Schrödinger's famous thought experiment involving a cat. In this hypothetical scenario, a cat is placed in a sealed box along with a device that has a 50% chance of releasing a lethal poison. Until the box is opened and the cat's state is observed, the cat exists in a superposition of states, both alive and dead. Schrödinger's cat is not meant to be a realistic depiction of feline mortality, but rather a stark illustration of the paradoxical nature of superposition and the measurement problem in quantum mechanics. It highlights the absurdity of macroscopic objects, like cats, existing in indeterminate states until observed. The Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg, argues that the wave function collapses upon observation, effectively selecting one outcome from the superposition of possibilities. However, the Copenhagen interpretation does not explain how or why observation triggers this collapse, leaving the door open for alternative interpretations and ongoing debate. The double-slit experiment, from its humble beginnings in Young's lab to its central role in quantum mechanics, has revealed a universe far stranger and more wondrous than we could have imagined. The wave-particle duality, the observer effect, and the measurement problem continue to challenge our intuitions and push the boundaries of our understanding. Quantum mechanics, with its probabilistic nature and counterintuitive predictions, forces us to confront the limits of our classical worldview. It compels us to question the very nature of reality, the role of the observer, and the meaning of measurement. While the interpretation of quantum mechanics remains a subject of ongoing debate, Its impact on our understanding of the universe and its potential to drive technological innovation are undeniable. The double-slit experiment, a beacon of quantum mystery, reminds us that the universe is full of surprises and that the quest to comprehend its secrets is far from over. As we delve deeper into the quantum realm, we can expect even more astonishing discoveries that will continue to shape our understanding of the cosmos and our place within it.